Everyone, today we're going to look at this paper or this subject, existence of convex Lyapunov functions. And let me check the source material. Yeah, the source material is this one, like Blancini and then Savartman. I just deleted the names. Stability of switch linear systems doesn't imply the existence of convex Lyapunov functions. This comes from the Automatical Journal and published in 08. So let's start with the basic definition. This is the third video in this playlist where we are discussing the convex Lyapunov functions and the stability conditions related to that. And definition 2.1, again, this numbering comes from that paper, the source material. Okay, so let me get another cover. Yes. So consider a system of the form. We have that type of switching or switch signal. And again, all of those, they need to agree on this equilibrium point, right? So for the system to be consistent, and consistent function, wait a second, not constant, continuous function, phi, or yeah, psi, Rn to R is said to be a Lyapunov function if we have these criteria. And then let me just check. Let me have that subset. So K1 and K2 from K, class K functions. This psi needs to be bounded by those functions, right? Okay, and the second part of the set of conditions, let's discuss them. Here we have the initial points, and let's say, I don't know how to make the sense of it, but we were used to having like x, v dots of x, for example, even that type of functions, we would be kind of okay with that, some type of positive function. And because this is positive and then this is negative, so basically we have like negativity, or yeah, we have that type of negativity and condition. So this v dots being negative, definite, and somehow implies this, or there is a case like if and only if relationship maybe, and this condition is related to how we would, not we, like in this case psi or psi would decrease. Okay, because here's I mean, this paper doesn't say it directly, but this alpha is almost like a KL type of function. So we know that as t goes to infinity, this will go to 0, right? This needs to, like for fixed volume in the first argument, as t goes to infinity, this will go to 0. So this decreases, like decreases in the second argument. Okay, and here we are talking about the properties of alpha function. And again, basically, like some type of KL function. Paper doesn't say it, but explicitly, probably to make the proof process like easier, they mention some additional properties, I think. Okay, so this was the Lyapunov function, expressed using class K functions, and then this, let's call this one a special class K function. And then, as we can imagine, exponential stability, v dot criteria must have a special kind of structure where not only it decreases, it needs to decrease in a structural way, like exponential way, right? So we can directly have like the structure of that alpha function that we would need to have here. If you will, we have k1, k2 after psi, and then we have, what was it, alpha function. We need to have like these 4 functions to determine the stability. Okay, and yeah, this alpha function would be in that type of structure, alright, when you have exponential stability. Exponential stability is the type of stability that can make things like easier Yeah. All right, or a bunch of advantages to that. And confinement set, let me get another color, just to spice things up. Confinement set is, we discussed that it has something to do with the retrieval set, but retrieval set, we often look at some time interval, right? But confinement set is what will the system be doing after t, right? From t to infinity, like till the end of the days, right? And then this is the definition. So we have a set of states satisfying the dynamics. Again, each initial condition takes the value from, or comes from, this given set of initial condition set, or arguments that we input to the confinement set. And for all t greater than or equal to t, right? I mean, since we discussed it, I'm glossing over that. And here, confinement set for stable systems, as t goes to infinity, right? What the system will do after 10 seconds, 100 seconds, like infinite seconds or something. And if it is stable, it will collapse, right? Basically, this is what we're saying here. And fundamental lemma of the paper. I am hoping this will be like a short video, and I will try to like keep it short and sweet. So, fundamental lemma of the paper. Let's discuss that. We have, again, the structure is not really important, and I'm mentioning it that way because the paper was talking about the switching and then switching type of continuous dynamical systems. But you can consider this a type of dynamical system. That's it. And with R be a compact set, R is not a reachable set, by the way, it's a set of initial conditions, right? If here's the statement, basically we have a set of initial points and then a dynamical system, right? Nothing much so far. If the system admits a convex Lyapunov function, if we have a possibility of finding a Lyapunov function which is convex, then for all t positive, you need to find confinement sets that corresponds to the given set of initial points, and then take the convex whole of it. Imagine it was like this, and then it turned out to be like something like that, and you need to take the convex whole. Right. This is basically what this is saying is the statement, and this set, you can consider this like confinement sets, or rather the set of initial points will not be a subset of, let's call quote unquote confinement sets. So what do we mean by that? Okay, for example, imagine this is R sets, okay, and then I'm thinking about something, wait a sec, and if we have, let me get another color. This will be kind of annoying to explain, but let's see what we can do. And here's the thing, it says for all t, this is, it doesn't say like there exists t or something, this says for t, so this is, okay, not an easy condition to satisfy is what I'm saying. Okay, so this is our set of initial conditions, and this sets, or rather this set will not be inside of the sets. which is, let's call quote unquote confinement set. Okay. It will not be like that, it will be like that. For all t, right? And here, if the system admits a Convex Lyapunov function, for all t, this you will not see something like this. Basically, this is what is being like stated here. So let's not think about that geometrically, maybe, and let's look at anytime geometry fails or our geometric intuition, even if there is such a thing, fails. Okay, let's look at the, let's say, algebraic rules and stuff, right? And here, this is the proof, lemma 2.5, 2.1, yes. I check if there was any error, and consider the Convex Lyapunov function, psi, and we have, first of all, okay, what do we have it so far? We have t, we have a set of initial points, and we have a dynamical system, and then we need to have a Lyapunov function, right? Okay. This says that let's define mu bar, right? So here we have this set of initial points, for example, and we look at every point and then we look at the maximum one, and by using that Lyapunov function as a measure, right? Like imagine Lyapunov function as some type of norm, for example. We look at the magnitude, quote unquote magnitude of that, or each of the points in this set of initial condition points. Okay, we called math cal r, all right, and consider Convex Lyapunov function, and then consider mu bar. All right, this is the definition of mu bar, and this comes from the, rather, we write it and then I basically answer why. If you are okay good student, and then if you're asking the question why, and okay, this box is answering that. So again, let's take it from the top. Consider the Convex Lyapunov function, psi, and here we have this variable. We introduce mu bar. We write that. Why we are able to write that? Let's discuss it. For the first part, and when I say first part, I mean that part. This comes from the definition of Lyapunov function. Like literally, we wrote this. You can just check and see. And okay, and here, for example, maybe you should write something like this. Okay. Here we're gonna look at, so there, this holds for every t, right? Possibly t. We are looking at only t equals t. We are looking at only one specific t, right? Time instant. Okay, we didn't change anything. We didn't change anything. Okay. And here we are looking at, for all the initial points, we are restricting that. We are looking at a given set of initial points. We are looking at those initial points, right? Then we are looking at, or we can say that due to the definition of confinement set, xt, this is like the beginning, basically, from t to like infinity. We are, let's say this is, at this time it looks like this, and then this goes, I don't know, collapse into a point or something. Anyway, that wasn't a good point to make, but due to the definition of this confinement set, because of definition, x of capital T should be in the set, right? And okay, so here looking at this, we are allowed to look at any initial point as long as it comes from this set, given set of initial points, like R set, right? And we are looking at this specific initial point. Okay, yeah, I mean, this is something we can do. Yeah, we can do it. And here I have like some type of color to make another point like in a way that is clear. So I didn't change anything that's like instead of all the initial points that comes from this set, I'm looking at only one specific initial point. Okay, and I basically eliminated that, right? Like everything stays same. Okay, so, and I highlighted that with red color. I am looking at the definition here. This is the definition. I'm basically putting mu bar. Yes, to signify some type of manipulations that we will be going through. And instead of saying x of capital T, like this, at the end of the day, this is like some variable, right? Like I can say, I don't know, John, or I can say like cat or something. And instead of that, I'm saying x. That is like nothing more than that. So this was the first part. Okay. Now let's look at the second part. Due to the, this is for the second part. Due to the definition or the properties stated in the lemma, like these two are given, right? Like directly they are given, and we basically arrive to that inequality, which was the second inequality here. Okay, so at this point, if you are cool so far, and just in your head delete that section. Now we first wrote this, and now we will discuss this. What we are trying to say is this is the given, like rather that expression is, I literally got this expression, that is it, and then put it in a box. I didn't do anything more than that. And it says that this implies, and again, one more really annoying typo. There needs to be like, let me switch. There needs to be in sign here. Okay, and yeah, like this. So instead of this set, we are looking at convex hull of the sets, and I didn't change anything other than these two sets, right? Like instead of these sets, I'm looking at convex hull, and then I'm saying that this inequality implies this inequality, same inequality, but the set of x values that this inequality is satisfied is changed. Now instead of this confinement set, I'm looking at the convex hull of the confinement set, and you should be immediately asking yourself why we are able to look at, or why this statement implies this statement. You should be saying that, hopefully. Consider the inequality. This is the inequality. Why do we have that inequality? This is the statement that we have, like we know this is why this is the case so far, and we will try to arrive at this statement, or we will show that this statement implies this statement. Okay, so here we know, and I'm looking at first and the third term, and also the set where this is the case. I am just looking at that part. Consider the inequality. Yeah, we are looking at this part, and since psi of x is convex. Okay, so let's, before saying anything, since the Lyapunov function is convex, before saying anything though, because there's something we need to remind ourselves of, if the system is convex Lyapunov function, so we need to assume we have the convex Lyapunov function, and then we will, using that information, we will derive and then see if we can arrive at this statement, right? We will try to show this statement is correct. Okay, this is the purpose of this proof, basically. All right. And I feel like I'm losing my voice though. Anyway, the type of thing that I'm doing for my views, that's crazy. So the Lyapunov function is convex, and since this is a convex with respect to x, and since this is the case, this set, what is this set? This is sub-level set, right? For this given scalar number. Again, like this is Rn to R, right? Lyapunov function, we know what that is. It's like almost like some type of norm in a way, right? Okay, so this set, like sub-level set, given mu bar, is also convex. This is, I mean, I'm not saying that we hold this truth like self-evident or something. I'm saying this comes from the fact that this is convex, right? We are assuming it is the case, and then we will arrive to the statement that we are trying to prove. Okay. Sub-level set of a convex function is convex set, so it's like a very concise way of stating that. And here, again, what we are doing is we have this, and we are going to show this statement is true. First of all, this is confinement sets, and this set is the sets where this inequality holds for every x point, or all, like this set is the set of x values that this given inequality, strict inequality, holds. Okay. We were looking at this set, right? So this set needs to be, I don't want to say like less than, but subset, or at most this set can be this set, right? Here, this set is all the points that satisfy the given inequality. So you cannot be like this set, there's no way this set can be like, greater than that, right? Covers that set or something. There's no way that can happen. And this, like the set of all the points that will satisfy this inequality, is subset of a convex function. Not subset, oh my god, like there's so many types, it's so annoying. Sub-level set of I should have said sub-level set of a convex function. Okay, and here's the thing. This is confinement sets. Here's the thing. This is a convex set, right? And we have a subset of a convex set, and when we have the convex whole of that subset of a convex set, and that needs to be a subset of that convex set. Okay, and that really makes sense. I mean, you can go and then show it. I was kind of tired, so I didn't like go through the computation, but it was like straightforward. Okay, and I'm not gonna make like a geometric argument or something. We have a set which is convex, and we are taking the sublevel or subsets, some subsets, and okay, I'm not gonna make a geometric argument, but in an abstract way I need to demonstrate something. So we have a convex set, and you get like any set, you can get any set you want, right? And when you take the convex whole of it, at most it can be that set itself, right? That is it. Like it cannot be something like this, for example, right? And this directly comes from the definition of a convex set. Convex set is the, for example, you give me any 2 points and then all the points between them need to be in this set. So basically this, let's say, implication comes from this property. Okay, and all right, so at this point we know that is the case, so I'm glad that I didn't have that error. We have in, this is what we know. Now we are here, right? And this implies that, and okay, we have this two numbers, I get it, but why? I mean, I'm saying that I'm looking at all the points. Like if there is an inequality, that would be satisfied in this set, and it can also be satisfied in oh my god, this is so annoying. Like there are just set x in convex. Okay, convex all of this confinement set. Anyway, if we have an inequality here, just let's focus on this part, and this needs to be satisfied in this set, then, and if the maximum is maximum with respect to some like norm is also in this set, then we can write that, right? That is that like a complicated thing that I'm arguing. If we assume, okay, this part is like really important now, okay, because this is the final part, and hopefully this will be a short video. So if we assume that is the case, R is a subset of the convex hull of the confinement sets, right? If that is the case, here, this is a proof by contradiction 101. We assume something, and if that implies something wrong, like false, then we will say that, oh, what we assumed was false, so the inverse of it, right, was correct. So this is the way we will show what we're trying to prove. And if, let's say this is the case, let's imagine that. So here, this is the inequality that we have, and if you look, this is exactly what I wrote here, but nothing more. And if I'm saying that instead of this set is a subset of that, then we would have inequality, not strict inequality, and such that we are looking at that set, all right, which is the subset of this convex hull of the confinement set. Okay, like this is very like intuitive. This is not complicated at all. Like basically what I'm writing is, let's say max x in set 1 max f of x in set 2, like if a set 1 is a subset of S2, then this is what you would have, that is it, because this is like a larger area. You can find something like larger than this, right? You have, not only you have S1, and you have also some other areas that you can look and maybe find something like larger than this, or larger than this. That is it. Like very, very simple to argue. Okay, here at the end of the day, and this is what we have. If we assume, and if that is the case, we would have that. Let's say a chain of inequalities. One is a strict inequality though, and here we will look at the first and the fourth, like the final part of that, like beginning and the end of that, let's say chain. What is that? this is strict inequality. If there was like less than equal to, then that will be another story. But this is strict inequality. And here's the situation. Our definition was mu bar was this. So basically what we just showed, 1 is greater than 1, and then this is not correct. And this is what we call in the business contradiction, right? And what was the reason of that contradiction? Here I highlighted as, with the red color. We assume that, so this, let's say, information lead to something like false. And this statement, since this statement is true, the only conclusion that we have is this statement was false, right? And we know that that is not correct. And then that's why when we invert it, we have not a subset of this convex of the confinement set. This is how we come to that information. And do you see how cute my QED is? This is therefore sign, of course, and this is what we were trying to prove, and then we prove that. So this was the source, and this, for the completeness, go through the lemma one more time. So we have a dynamic system, and then we have a set of initial conditions. We should be compact. I'm sure that there must be a reason for that. And if the system admits a convex Lyapunov function, then for all t, basically this convex hull of this confinement set will not cover that R set of initial points. That is it. And if we have a convex Lyapunov function, this situation will not happen. So you can consider something like this, for example. I don't know if that would be like a good thing to argue, but let's say this is R, like that R, like set of initial points. If we can have a convex Lyapunov function, so it's almost like the type of stability that you could think of, right? So this will, like all the points will get close to the equivalent points. But here, for the stable systems that are like stable in a way that the stability can be only proven with Lyapunov functions that are not convex, they are kind of weird in a way that they will, like I'm talking about the type of stable system that you cannot find a convex Lyapunov function, and they will first, for example, let's look at when this is t equals 0, right? Or let me get another curve. This is basically t equals 0. Oh my god, come on. Let me get blue, t equals 0. And this is t equals 1, for example. Of course, what I'm arguing is like very like almost childish, but hopefully we get somewhere. And t equals, let's say, 100 is something like this, for example. It will just move. Instead of going like that, it will go and then it will go up and then down. Something like that. So this is like some type of weird thing is happening in this side. And I am talking in a very loose way, like in a very informal way, right? Got it. Because now we know each other, so we can be, get rid of that formality. I feel very close to my viewers. All right. And then using that, rather using this lemma, we will look at some type of systems, and I think they are generally in this paper, or there's another paper that I will be discussing maybe in the next video or something, and hopefully that will be also a short video. It will be a switching type of system, and we will look at whether or not we can find a convex Lyapunov function for that type of system, right? And looking at that property, or looking at this like lemma, we will also, and then looking at the properties of the system that we have, we will derive some type of conditions, set of conditions that are easier to like check, like analyze, right? That is it. And don't forget to subscribe, and please leave a like. Thank you.